Right, good morning, good afternoon, good evening, class. Today in calculus, we studied the squeeze theorem today. Okay, so this kind of builds off of what we talked about the other day. The squeeze theorem basically states the following: if I have three functions, f of x, g of x, and h of x, and all these functions follow this hierarchy where f of x is less than or equal to g of x, and g of x is less than or equal to h of x, and the following is true: the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x, and this limit exists, then the following must be true. So then the limit as x goes to a of g of x is also equal to the same thing. Okay, so effectively, this is at some point a. At a point a. Essentially not at, should be near a point a. This is near x equals a. Okay, it doesn't have to necessarily be true when x is equal to a, but when x is near a, then this is the squeeze theorem. So if f of x, if f of x is less than g of x and less than h of x, and the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x that exists, then the limit as x goes to a of g of x has to also be the same limit. Okay? So you can think of it as basically one function is squeezing, f of x and h of x are squeezing g of x between them. They're like a sandwich. Sometimes it's called the sandwich theorem or the pincer theorem. Okay, let's go through some examples to help illustrate this. So here's an example. So let's find the limit as x goes to 0 of x squared times sine of 1 over x. Yeah. From previous lessons, we can break this up as follows, because this is really just a product of functions, so we can say the following. Now this is equivalent to this times x goes to 0 of sine 1 over x. But we run into an issue. This particular limit at the moment does not exist when x is equal to 0, because we got a division by 0 here. This will give me a division by 0. So this gives us some problems. However, we're going to use a squeeze theorem on this. So I'm going to write the following. So sine 1 over x. Now, sine 1 over x, we know that the behavior of sine does the following. Sine 1 over x is always greater than or equal to -1, and it's also always greater or less than or equal to +1. And this is always true. Okay, so we know sine 1 over x sort of fluctuates between these two. Now what's neat about inequalities, and this is something that I don't think it was ever really discussed, but it's really cool, is that I can take the entire inequality, and as long as I multiply everything by a positive number, the inequality doesn't change. So I'm going to multiply it by the following: x squared. X squared happens to always be positive. So this will then become the following: negative x squared less than or equal to x squared times sine 1 over x, which is less than or equal to x squared. Okay. Now I can say the following, or I can do the following next. I can say, what is the limit as x goes to 0 of negative x squared? Okay, and this has to be less than or equal to the limit as x goes to 0 of x squared sine 1 over x, which has to be less than or equal to the limit as x goes to 0 of x squared. Okay. This is great because what do I know about this particular limit? Well, if I put 0 in for x squared, this ends up becoming 0. Okay. Over here on this side, if I calculate this one, so I put 0 in for x, this gives me also 0. So it basically means that this limit has to be 0. There's no other number that can really be between 0 and 0. It has to be equal to 0. Okay, so then we can say that by the squeeze theorem, limit as x goes to 0 of x squared sine 1 over x is equal to 0 by the squeeze theorem. Okay? And we can also calculate this ourselves, or we can graph it just to see if it, just to show that it is actually correct. Okay, so here's Desmos, or handy dandy graphing calculator. So let us graph x squared times sine 1 over x. Okay, then I'm going to graph x squared and negative x squared. Alright, so it doesn't look like much right now, but let's zoom in. Zoom in. There you go. As you can see, it looks like our function, sine x, that's this one here, the red line, sine 1 over x is being squeezed by positive x squared and negative x squared. And let's zoom in some more. And it is being squeezed until it is effectively equal to 0 once it gets to x equals 0. Okay? And that's how we use the squeeze theorem. Very simple, very easy to use. All it requires us is to basically pick two functions that will effectively squeeze the original function. Okay? Very useful when calculating trig. When calculating limits for trig functions, because trig functions exhibit that kind of periodic behavior. Alright, so that basically does it. That's the squeeze theorem. Tomorrow we'll talk about something new.